Hello viewers, welcome to the session on food technology. Today's topic is food pigments. Introduction. Food pigments are naturally occurring compounds present in plants and animal tissues. It plays a very important role in enhancing the aesthetic appeal of food. Until the discovery of the synthetic dyes, man has been relying on pigments extracted from plants, animals and minerals as food colorants. The plant kingdom, with its multitude of colors, generates vast interest among many researchers and is most widely studied as major source of food pigments. Flavonoids, carotenoids and chlorophyll are the major contributors to the natural colors of most plants, with beta-leans and curcumin playing a minor yet significant role. To understand more about food pigments, their sources, structure and stability, the topic is divided into 8 sessions, that is, sources of natural pigments, classification of pigments, flavonoids, carotenoids, chlorophyll, beta-leans, caramels and heme pigments. Sources of natural pigments. Pigments are found widespread in nature from the simplest prokaryotic organisms like cyanobacteria and throughout the kingdoms of fungi, plants and animals. Sources of natural pigments are flowering plants, Magnoliophyta of the plant kingdom, scale insects cochineal and lac, fungi Blackcassiella trispora and Moniscus species, and cyanobacteria Orthospira species. Plant pigments are used widely and are sources of chlorophyll, flavonoids, carotenoids and beta-leans. Chlorophyll is found abundantly in the aerial parts of plants such as leaves. Anthocyanins are a group of flavonoids that provide the red-purple shade of many fruits, in particular berries, for example strawberries and blackcurrant. Carotenoids are found in sweet potato, carrot, pumpkins, dark green leafy vegetables, Dunaliella salina, which is an algae, and Blackcassiella trispora, which is a fungus. Other important classes of pigments are the anthraquinones found in root of Morinda angustifolia, allolatics, senna, rhubarb, fungi, lichens and cochineal, and beta-leans which are found abundantly in beetroot. Heme pigments are responsible for the color of meat in animals. Myoglobin is found in the muscle tissue, whereas hemoglobin is the pigment responsible for the color of blood. Fresh meat and blood are the major sources of these pigments. When sugars are treated under anhydrous conditions with heat or at high concentrations with dilute acids, caramelization occurs with the formation of amber to dark brown colored caramel pigments. Classification of pigments. Based on their solubility, pigments are classified as water-soluble and water-insoluble pigments. Chlorophyll and carotenoids are water-insoluble in nature, whereas flavonoids and beta-leans are water-soluble pigments. Based on the sources, they are classified as food pigments of plant origin, animal origin and synthetic pigments. Pigments of plant origin include chlorophyll A, chlorophyll B, carotene, lycopene, anthocyanin, flavonols, tannins, betanin and beta-xanthins. Pigments of animal origin include heme compounds such as myoglobin, oxymyoglobin, metmyoglobin, nitrosomyoglobin, nitrosometmyoglobin, globin myohemochromogen, which range between purplish red to brownish red in color, choleglobin, nitrihemin and verdoheme, which are green in color, and bile pigments which are yellow in color. The color of these pigments greatly depend on the state of iron, that is, ferrous or ferric state. Synthetic colorants include brilliant blue FCF, indigo, carmine, sunset yellow FCF and fast green FCF. Based on their chemical structure, they are classified as tetrapyrols, tetraterpenoids, O-heterocyclic compounds or quinones and N-heterocyclic compounds. Heme compounds and chlorophylls are grouped under tetrapyrols, carotenoids under tetraterpenoids, flavonoids or phenolics under quinones, and betaleins under N-heterocyclic compounds. Flavonoids. Anthocyanin, chalcone, and flavones belong to a group of compounds collectively known as flavonoids. Anthocyanins are pigments found in a wide variety of edible plant materials such as skin of red apples, plums, and grapes, in addition to strawberries, cranberries, raspberries, elderberries, blueberries, and red cabbage. The major source of anthocyanins is the grape skin. Extraction of anthocyanins generally involves the use of an alcoholic solvent. One of the conventional methods of extracting anthocyanin from macerated plant materials involves the use of low boiling point alcohols such as methanol, ethanol, and N-butanol, which have been acidified with mineral acids like HCl. Anthocyanins impart blue, purple, violet, magenta, red, and orange colors in food. The word anthocyanin is derived from two Greek words, anthos, which means flower, and kainos, which means blue. The basic structure of flavonoid group has the characteristic C6C3C6 carbon skeleton. The color of the subgroups depend on the presence and number of substituents attached to the molecule. Applications of anthocyanins in food is restricted due to their ability to participate in a number of reactions resulting in its decolorization. These include reactions with ascorbic acids, oxygen, hydrogen peroxide, and sulfur dioxide to form colorless compounds. Formation of complexes with metal ions and proteins, and hydrolysis of sugar moiety to form unstable anthocyanidins. Anthocyanins are also sensitive to pH, being more stable at lower pH. In addition, the anthocyanin colors vary with change in the pH. At pH 1 and below, the anthocyanin pigments gives an intense red but becomes colorless or purple when the pH is increased to between 4 and 6. Meanwhile, the pigment turns a deep blue when the pH is between 7 and 8. Further increase in pH sees the anthocyanin pigment turning from blue to green and then to yellow. Such variation in color has been attributed to structural transformation in response to changes in pH. The stability of anthocyanin in the lower pH range means that anthocyanins are best suited for use in foods of low pH. The degree of unsaturation in anthocyanidin structure makes it susceptible to oxidation, changing the color from purple to brown. Stability of anthocyanins is higher at lower water activity, that is 0.63 to 0.79. They are also susceptible to photodegradation. Generally, increased hydroxylation decreases the stability, while increased methylation increases the stability of anthocyanins. Also, the unsaturated nature of the anthocyanidin structure makes it susceptible to oxidation. At higher concentration of sulfur dioxide, that is 0.8 to 1.5%, bleaching of anthocyanin takes place, while some metal ions such as calcium, iron, and aluminium protect the pigments from discoloration by forming complexes. Enzymes, glycosidases and polyphenol oxidases hydrolyze glycosidic linkages yielding sugar and aglycones characterized by discoloration. Anthocyanins are currently being used to provide a natural red or blue coloring for foodstuffs. Successful applications of anthocyanins include the coloring of canned fruits, fruit syrup, yogurt, and soft drinks. Commercial anthocyanins have also been used to intensify the color of wine. Carotenoids. Carotenoids are water-insoluble pigments found in all higher plants and some animals. Animals cannot synthesize carotenoids, so their presence is due to dietary intake. For example, the pink salmon flesh owes its color to carotenoids. Carotenoid is derived from the word carota, which means carrot, and xanthophyll is derived from the Greek words yellow and leaf. Together with anthocyanins, carotenoids are the most complex class of natural food pigments with around 750 different structures identified. Plants such as carrots, vegetable oils, apricots, dark green leafy vegetables, kale, spinach, broccoli, grass, alfalfa, oil palm and nettle are sources of carotene. The predominant carotenes are alpha and beta carotene and other carotenes such as phytoene, phytofluene, gamma carotene and lycopene, which are all precursors in the biosynthesis of alpha and beta carotene. Carotenoids impart red, orange and yellow color to the plants. Carotenoids can be divided into carotene, which are hydrocarbons containing only carbon and hydrogen, and xanthophylls are oxygenated derivatives which are made up of carbon, hydrogen and oxygen. They are made up of 8 isoprenoid units joined in such a manner that the arrangement of isoprenoid units is reversed at the center of the molecule, so that the two central methyl groups are in a 1,6 positional relationship and the remaining non-terminal methyl groups are in a 1,5 positional relationship. All carotenoids may be formally derived from the acyclic C40H56 structure having a long central chain of conjugated double bonds by hydrogenation, dehydrogenation, cyclization, oxidation or any combination of these processes. Carotenoids, like other pigments, are susceptible to oxidation mainly due to their conjugated polyene chain. Thermal treatment of carotenoids in a presence of oxygen results in the formation of volatile compounds, larger non-volatile compounds, cis isomers and oxidation products. Exposure of carotenoids to acids produces ion pairs which later dissociate to form carotenoid carbocation. Oxidation of carotenoids by free radicals such as singlet oxygen leads to the formation of beta-carotene 5,8 endoperoxide and beta-carotene 5,6 epoxide. Lycopene. The structure of lycopene is similar to carotenoids with molecular formula C40H56. Being a precursor in the biosynthesis of beta-carotene, lycopene can be expected to be found in plants containing beta-carotene, usually at a very low concentration. The best known sources of lycopene are tomatoes, watermelon, guava and pink grapefruit. In solutions, lycopene is orange and not bright red as in the tomato. Lycopene is hardly used as a colorant because it is a rather expensive pigment and is very prone to oxidative degradation. Lutein and zeaxanthin are oxygenated carotenoids with the molecular formula C40H56O2. The name lutein is derived from the Latin word for yellow. Commercially, the most interesting source is Aztec marigold, in which lutein is primarily found esterified with saturated fatty acids, lauric, myristic, palmitic and stearic acid. Lutein made from Aztec marigold also contains some zeaxanthin, typically less than 10%. Containing only 10 conjugated double bonds, lutein is more yellowish green than oil palm carotenes. Annatto. Annatto is both the name of the colorant and the tree providing the colorant. Other names of the tree are lipstick tree and achiote. The colorant is extracted from the seeds, which are covered by a red resinous coating containing the pigments. The main pigment is bixin, which is a cis isomer. Smaller amounts of transbixin, norbixin, which is a demethylated bixin, and trans-norbixin are also present. Annatto may be extracted using either of three methods, that is extraction with hot vegetable oil, extraction with organic solvents or extraction with alkali. Extraction with vegetable oil or organic solvents gives a colorant containing bixin as the main coloring principle, whereas extraction with alkali leads to saponification of bixin, yielding the water-soluble Norbixin, which may be precipitated by acid to give a powder. Norbixin is used to color cheese, example cheddar cheese, because it binds to the protein. It may also be used to color beverages with neutral pH, for example flavored milk drinks, but not with low pH because of the precipitation. Annatto is slightly more reddish in application than beta carotene. Paprika. Paprika is a well-known spice made from the fruit pods of Capsicum annuum. Paprika contains the orange-red pigments capsanthin and capsorubin and a number of yellow pigments, most notably violaxanthin, zeaxanthin, beta-cryptoxanthin and beta-carotene. Next session under this topic is chlorophyll. Chlorophyll is the green pigment utilized by all higher plants for photosynthesis. It is derived from the Greek words for green and leaf. The most important member of the tetrapyroles is chlorophyll, which are green pigments found in all higher plants, algae and photosynthetic bacteria. Chlorophyll is derived from the porphin and has a 4-cyclic tetrapyrrole bridged by single carbons with coordinated magnesium in the center. Following these are pyrrole carbon atoms on the periphery of the porphin, which are also bridged by carbon atoms. Substituted porphins are called porphyrins as displayed on the screen. In plants, there are two forms of chlorophyll, chlorophyll A and B, which only differ in the substitution at C3 position of the tetrapyrrole ring. Chlorophyll A has a methyl group, whereas chlorophyll B has a formyl group. It is water insoluble in nature and can be extracted with the use of organic solvents. Chlorophyll can be made water soluble by saponification, in which case it is called chlorophyllin. The coordinated magnesium is easily lost during extraction and processing, especially under the action of acid, and is displayed by hydrogen atoms, yielding a yellow-brown pigment pheophytin. Copper forms a complex with pheophytin. These complexes are often referred as copper chlorophylls or copper complexes of chlorophyll or copper pheophytins. Copper chlorophyll behaves very much like chlorophyll, except that it is more of brighter green and much more stable, since copper is not easily displayed. Chlorophyll can be degraded by chlorophyllase to form chlorophyllides and pheophorbides. However, the enzyme is active between 60 degrees to 80 degrees Celsius. Structurally, chlorophyll B is more stable than chlorophyll A due to the electron withdrawing effect of C3 formyl group. pH plays a vital role on the stability of chlorophyll, where the stability is higher in alkaline pH than acidic pH. Chlorophylls oxidize when dissolved in alcohol or other solvents and exposed to air. This process is called allomerization. Chlorophyll can act as a sensitizer and generate singlet oxygen, while carotenoids quench these free radicals and protect the plant from photodegradation. When the protection is lost, chlorophyll under light and oxygen are irreversibly bleached. The process results in opening of tetrapyrrole ring and fragmentation into low molecular weight compounds such as methyl ethyl malayamide. Betalenes. Betalenes and anthocyanins have similar color. They are of two types, beta-cyanin and beta-xanthin. Beta-cyanins are red in color and beta-xanthins are yellow in color. Beetroot and amaranth leaves are good sources of betalenes. When compared to anthocyanins, betalenes are stable to a wider pH range. They are present in the vacuoles and are water soluble in nature. The general formula of betalenes represents condensation of primary or secondary amines with beta-limic acid. Beta-cyanins are optically active and have a chiral carbon at C2 and C15 position. Hydrolysis of beta-cyanin leads to either betanidine or isobetanidine or a mixture of the two isomeric aglycones. Beta-xanthins are present as indica-xanthin and vulgaxanthin 1 and 2. Beta-xanthins differ from beta-cyanins, where the indole nucleus is replaced with an amino acid, where it is proline in the case of indica-xanthin and glutamic acid in the case of vulgaxanthin. Under mild alkaline conditions, betanin degrades to beta-lamic acid and cyclodopa 5-O glucoside. These two degradation products also form during heating of acidic betanin solutions or during thermoprocessing of products containing beetroot, but more slowly. Decrease in water activity will decrease the degradation rate of betanin. As in the case of other pigments, betalains are also sensitive to oxidation, which accelerates in the presence of light. Caramels. Caramels are water-soluble food colors. It is made by heat treatment of carbohydrates, in general in the presence of acids, alkalis or salts, in a process called caramelization. It is produced from commercially available nutritive sweeteners consisting of fructose, dextrose, invert sugar, sucrose, malt syrup, molasses, starch hydrolysates and fractions. It is more fully oxidized than caramel candy and has an odor of burnt sugar and a bitter taste. Its color ranges from pale yellow to amber to dark brown. Caramel color is one of the oldest and most widely used food coloring and is found in many commercially produced foods and beverages, including batters, beer, brown bread, buns, chocolate, cookies, cough drops, spirits and liquor. They are widely used in chocolate flavored confectionery and coatings, custard, decorations, fillings and toppings. Soft drinks, especially colas, have caramel as coloring and flavoring agent. Caramel color is widely approved for use in food globally, but application and use level restrictions vary by country since caramel at higher levels are harmful. Heme pigments. Heme pigments are responsible for the color of meat. Myoglobin and hemoglobin are the primary pigments present in meat. The colors imparted by these pigments and their secondary compounds are purplish red, bright red, brown, reddish brown and green. The color of the pigments depends on the state of iron, state of globin, state of oxidation and mode of formation. Myoglobin is a globular protein consisting of a single polypeptide chain and is comprised of 150 amino acids. The molecular mass is 16.8 kg. The protein portion of the molecule is known as globin. The chromophore component responsible for light absorption and color is the porphyrin known as heme. The porphyrin ring is formed by 4 pyrrole rings joined together and linked to a central iron atom. Thus, myoglobin is a complex of globin and heme as displayed on screen. Hemoglobin consists of 4 hemoglobins linked together as a tetramer. When molecular oxygen binds with myoglobin, oxymyoglobin is formed, which has a bright red color, whereas deoxymyoglobin is purplish red in color. When oxidation of myoglobin occurs, the iron atom is converted from ferrous to ferric state, forming metmyoglobin, which is brown in color. In the presence of hydrogen peroxide, ferrous or ferric site of heme forms choleglobin, a green colored pigment. Lipid oxidation accelerates pigment oxidation, which can be prevented by addition of antioxidants such as ascorbic acid and vitamin E. Irradiation of meat changes the color of the meat since iron in myoglobin is susceptible to change in chemical environment. To conclude, food pigments have an important role as colorants in food industry in enhancing the aesthetic appeal. Pigments are found in minute microorganisms as well in the animals and plant kingdom. The structure and stability of pigments determine the retention or loss of color. Various factors influence the stability of pigments, which include temperature, pH, oxidation and photodegradation. Apart from imparting color, few of these pigments also serve as antioxidants. Therefore, pigments are an important part of food. Thank you.